Now students, today we will solve example number 1.8 and example number 1.9. Before we start these two examples, let us first revise the previous topic. We have studied earlier that if the charge is positive, then the electric field will be moving outward, and if the charge is negative, then the electric field will be moving inward. Also, near the charge, if we select any point P, then the distance is small, and if the charge is considered away from any point, let us take a point Q which is far away than point P. In this case, the electric field at point P will be strong and the electric field at point Q will be weaker. One more thing, if there is an electric field which is shown by parallel lines, then this type of electric field is considered uniform electric field. If the electric field is like this, moving away from each other, the arrows, their distance becomes larger as they move away. Or if it is like this, then this type of electric field is considered non-uniform electric field. Other important thing is, if a charged particle is placed in the electric field, suppose let this is the charged particle Q in an electric field, then the force will act in the electric field on the charged particle according to formula F is equal to Q into E. In this case, this charged particle experience the forces, and so it will move in the direction of electric field if this is a positive charge, and if the charged particle is negative, then it will move in the opposite direction of electric field due to this force. Now in this example, given that the electric field is in the upward direction, and you can see the electric field, they are parallel to each other, means the electric field applied is uniform, and a charged particle, that is electron, is placed inside the electric field, and so due to force acting on this charged particle due to electric field will be in the opposite direction. As electron is negative charge, in an electric field it will move in the opposite direction. Here we will neglect the effect due to gravitational force, and so the only force acting on this electron will be electric force, that is F is equal to Q into E. Now suppose if this charged particle covers the distance h in the electric field, due to this force, so it will take some time to reach from one point to other. This distance covered by the charged particle is given 1.5 centimeter. Also, the strength of electric field is given, which is 2 into 10 raised to 4 Newton per Coulomb. Mass of electron, that is also given, 9.11 into 10 raised to minus 31 kg. So here we want to find how much time will this electron take to cover this much distance of 1.5 centimeter. So first we will find the time taken by the electron, and then in next part we have to find the time taken by the proton for similar type of situation. This situation is shown in the next figure. You can see here the electric field is reversed. Earlier it was in the upward direction, now it is in the downward direction. Earlier an electron was placed in the electric field, now a proton is placed in the electric field. So as I said earlier, that if a positive charge is placed in an electric field, then it will move in the direction of electric field due to the same force, that is F is equal to Q into E. We know that the charge of an electron or a proton is same, that is 1.6 into 10 raised to minus 19 Coulomb. The only difference between proton and the electron is their masses. The mass of electron is very less compared to the mass of proton, and so the acceleration of electron will be much more compared to that of proton, and so time taken by electron to move or to cover this much distance of 1.5 centimeter will be less, and the time taken by the proton to cover the same distance will be more. So now let us start the example. As the charged particle is placed in the electric field, this force will act. F is equal to E into E. Here the charge is E, because as I said that the charge of an electron or a proton will be same, so it is taken as E. So this equation number is 1. Also, due to this force the charge will move, and we know that when there is an acceleration on a particle, we can use Newton's second law, F is equal to ma. So these two forces, F is equal to E into E and F is equal to ma, will be same. So if we'll compare equation number 1 and equation number 2, and if we'll make the subject A, then we'll get this equation. Simply you have to compare this two, that ma is equal to E into E, and then if you'll make the subject A, you will get A is equal to small e into capital E upon m. Now we got the acceleration. These values E, capital E and m, these are given. Now we will give this equation of acceleration as number 3. We will not put any values at present, we will put all the values at last. Now we want to find the time. Acceleration is already obtained. Now using kinematic equations which you have studied in 11th standard, that distance is given, which is denoted here by h, time is to be obtained, acceleration is known to us. Initial velocity of the particle is 0, so this term will not there because initial velocity is not there. So distance is equal to half of at square. So distance h is equal to half of at square. Now make the subject t, you will get t is equal to root of 2h by a. Now acceleration from equation number 3. If we'll put this acceleration here from equation 3, this equation will take the form t is equal to root of 2h into m upon small e into capital E. So here we have obtained a general equation of t. Now if we want to find the time taken by the electron to cover that distance h, then simply we have to put the mass of the electron here. Other values will be same if it is electron or a proton, but here we want to find the time for an electron, so mass will be of electron. And so after putting these values which are given, all these values are given, mass is also given, h is also given, e is also given, capital E, that is electric field, that is also given. So just put the values and calculate, you will get this answer. Now if you want to find the time taken by the proton, then simply what we have to do, we have to put the mass of proton. Other values are given, and so after calculation you will get the time taken by the proton to cover that much distance, that is 1.5 centimeter. Here you have to take care about one thing, that when you put the values while calculation, you have to consider SI system of unit. Means here the height h is given 1.5 centimeter. So you have to convert this 1.5 centimeter into meter, and that also you know how to convert it. So in this way you will get the time taken by the electron also, and that by the proton also. See, the time taken by electron is 10 raised to minus 9 power, and time taken by the proton is 10 raised to minus 7 power. So definitely here the time taken is very small. So electron will take less time while proton will take more time, as proton is quite heavier considering the electron. So here we complete this example, and our next example will be example number 1.9. Now students, earlier we have obtained the force on a particle kept at a point due to other charged particles by using vectors. So here also the process will be similar, but in place of force we are going to find the resultant electric field at a point. In this example, two point charges q1 and q2 are given. They are having charge plus 10 raised to minus 8 coulomb and minus 10 raised to minus 8 coulomb. You can see here the magnitudes of this charge is same. One is having 10 raised to minus 8 coulomb, the other is also having 10 raised to minus 8 coulomb. The only difference is that one is positive and the other is negative. So these two charged particles, they are given, their positions are shown in the figure. These two charged particles, they are placed at zero point 0.1 meter apart from each other. Now here we are going to find the electric field due to these two charged particles at point A, at point B and at point C. We know that due to positive charge the electric field will be moving out, while due to negative charge the electric field will be towards inward. So if we want to find the electric field at point A, then this electric field at point A due to these two charges will be in the same direction, and so the resultant electric field will be the summation of the electric field due to charge Q1 and due to charge Q2. As this point A is at the center, the distance of A from charge Q1 will be 0.05 and the distance of this point A from charge Q2 is also 0.05, because the total distance between these two charges is given 0.1 meter. So this distance will be half. Now now we are supposed to find the electric field at point A also, at point B also and at point C also. First we are going to find the electric field at point A. So for that, as I explained, the electric field at point A is due to the charged particle at point 1 as well as due to charged particle at point 2. So the magnitude of electric field at point A is the summation of these two electric fields due to both the charges. Here the plus sign is kept because these electric fields are in same direction. Also, the magnitudes of electric field at point A due to both the charges will be same, will be equal. It is because the distance as well as the magnitude of charge is same from that point A, and so the resultant electric field is twice of EA1. Now we know the formula of electric field due to any charge. Electric field due to any charge E is equal to K Q by R square. So here also if we'll put the formula of electric field, then we'll get it as K Q1 upon R square. Here there is a printing mistake. In place of simply RA1 we have to put here square also. So this is the formula for electric field and 2 as it is. Now value of K is known to us. It is 9 into 10 raised to 9. Magnitude of charge is given. Also the distance is given. So by putting these values, finally we will get this answer for this electric field, and when it is multiplied by 2, this 2, we will get the electric field at point A. Now we obtained the electric field, but its direction is also important. Here simply there is a magnitude, but we know that the electric field is in this direction. You can see here in the figure, it is in this direction, which is positive x direction, and hence here it is given that the electric field is along the positive x direction. So we obtain the magnitude of electric field and its direction at point A. Similarly, now we are going to find the electric field at point B. Here in figure it is shown that point B is kept at this point. Again the distance here is 0.05 meter. So at this point B, the electric field will be due to both the charges, that is due to charge Q1 also as well as due to charge Q2. But the electric field due to this charge, that is Q1, is in this direction because it is positive charge. So electric field will be moving away, while due to negative charge the electric field will be towards this charge. And so as one electric field is in this direction and the other electric field is in this direction, that means the direction is opposite, so resultant electric field will be difference of both. Now here we can see from the figure that this charge particle is quite near to this point B, and this charge particle is quite far away from point B. So as this distance is large, the electric field due to charge particle Q2 will be very weak compared to the electric field due to charge particle Q1. So this electric field due to Q1 will be strong, and so the resultant electric field, its direction will be this, that is towards the negative x direction. So now let us see the calculation part. Again, the resultant electric field at point B is summation of both these electric fields. Here you can see this equation is in vector form, and so as a vector here we have to add these two, but after that we are going to find the magnitude. So here electric field due to first charge particle is towards negative x direction, so the sign is minus, and due to second charge particle the electric field is in positive direction, that is positive x direction, so it is plus. Now putting the formulas of both the electric field, K Q1 upon RB1 square due to this, and second is K Q2 upon RB2 square due to this. In earlier case the distance were same, but here the distance are not same. And so the next part of this will be like this. Here this K and Q1 as well as here this K and Q1, they are taken out common because the magnitude of Q1 and Q2, they are same, so they are taken out, but the distances are not same, so they were kept inside. So taking out this common, we'll get this step. And now putting the values, we know the value of K, we know the value of Q, we also know the value of RB2 as well as RB1. You can see this from the figure also, that the distance RB2 means from B to 2 will be this, and distance RB1, that is from B to 1, that is given. So this distance as well as this distance, if we'll put and calculate, we will get the answer, and that will be 3.2 into 10 raised to 4 Newton per Coulomb, and direction is negative as I said earlier. And then finally at point C, electric field at point C. Let us see first figure, that electric field at point C, that is this point, will be due to this charge particle as well as due to this charge particle. But electric field due to the charge Q1 will be in this direction, and electric field due to this charge which is negative, so it will be moving towards it. So these are the two electric fields. Electric field at point C due to point 1, so it is EC1, and this is the electric field at point C due to 2, so it is EC2. And then finally the resultant electric field at point C will be in this direction. So we will apply the similar step which we have done in the earlier example number 1.7, I think so. So one electric field is in this direction, other is in this, an angle between these two will be 120. Why? Because this forms an equilateral triangle, so this angle will be 120 from the geometry of the figure. And then finally, to find this resultant electric field, we can apply the formula which we have used earlier for the forces also. So electric field at point C is square root of this first electric field square plus second electric field square, then plus 2 into this term. Here this angle is 120, so cos 120 is this electric field and this electric field, their magnitudes will be same. The magnitude of this as well as this is same, and so here it is taken out common. You can see here also this term. Then after calculation, simple calculation is there. I will not explain you more about this because we have done this type of calculation in earlier examples. And finally the resultant electric field, its value will be this much. Its direction is positive, that you can see from the figure also. You can see here the direction is towards positive x direction.